All right, so we want to welcome everyone to this very special chemistry seminar coming to you from Andrews University Chemistry Department. And my co-host today is Alana. She's a senior biochemistry major, and she is also the editor-in-chief of the Student Movement newspaper here on the campus. And I think she's perfect to be my co-host for this lecture. She has a lot of interest and practice and publications in creative writing. She will introduce our speaker after we hear from President Loxton and Provost Arthur. That's my introduction. And so I pass it on now to our president, Andrea Loxton.
Thank you very much, Desmond, and welcome everybody. It's good to see you all here. I know some of you are here from Andrews, but I know that we are having people join us from all around the country. So that is excellent, and thank you so much for doing that. As you know, this is the second installment of the Dwayne Ford Lecture Series in the Andrews University Department of Chemistry and Biochemistry for the fall semester. And I'm particularly delighted to welcome our speaker today. As we know, Dr. Hoffman is a Nobel Prize winner in chemistry from 1981, and that is amazing. In addition to that, I want you to know my PhD is in literature. And so I was extremely excited to know that you have published 7 volumes of poetry, 3 plays, and 6 nonfiction books. In fact, I spent half an hour earlier today checking on some of your plays and poetry.
Yes,
and,
make sure your library has them.
well, you know, I have announced my retirement at the end of this year, so I've now put your name on my list of things to do after retirement. But what I appreciated in a quick look at what you were doing is that way that you really have carved out this area between science and literature, and also your own personal experience that is just running all the way through your poetry and your literature. So we are extremely delighted to have you here today, and I know that we're all going to be extremely blessed by your presentation. So thank you so much for joining us.
Thank you.
Very good, very good.
And Dr. Hoffman, let me add my welcome to you as well. Welcome to Andrews University. It's virtual, but it's no less real that you're here with us. You would find during your lecture, when we have time for conversations, that Andrews has the best students. Andrews University, a world-class for its diversity, but also world-class because we have students from all 50 states and from every continent, and they're part of this great community. And you'll find that what you share with us this afternoon will be very enriching. We are very generous people, and look out in the mail in the next few weeks. We'll send you a gift. I'm not going to tell you what it is. It'll be the grandest surprise. But do me one favor. When you receive it from us, turn on your camera and your phone and send back to us your expression when you see what we've sent to you. We want to see what your expression would look like. So welcome to Andrews, and we're looking forward to your talk with us this afternoon.
Thank you very much. Thank you.
Good. And then finally, our introduction by Alana.
All right. Well, let's get into it. Professor Roald Hoffmann was born in Poland in July of 1937. A poet, chemist, and philosopher, Professor Hoffmann arrived in the US in 1949 and studied chemistry at Columbia and Harvard universities, the latter at which he earned his doctorate, where he worked on molecular orbital theories. He has been a professor at Cornell University since 1965, where he is currently the Frank H.T. Rhodes Professor of Humane Letters Emeritus. He has received many honors for his major contributions to science over the course of his career, perhaps most notably, well, of course, most notably, his 1981 Nobel Prize in Chemistry. As mentioned, Professor Hoffman is also an avid poet and writer, and in his most recent play, Something That Belongs to You, he reflects on his experiences during the Holocaust. And in two of his books, Roald Hoffman on the philosophy, art, and science of chemistry, as well as Beyond the Finite, the Sublime in Art and Science, he explores the nuanced intersection between the two mentioned disciplines. Today, Professor Hoffman is here to be leading an interdisciplinary discussion that connects chemistry, culture, literature, and the humanities. So without further ado, it is my considerable honor to introduce Professor Roald Hoffman, teacher, writer, and chemist.
Thank you very much. Let me just connect on here with my presentation, just so that works, if I can find it.
Yeah, you should be able to
Well,
screen.
I don't quite see it, but let me go back first and the same thing as last time
Okay,
and open it. Hold on, just please with me.
not a problem.
So I have to reduce the size. I
Okay.
now have to go back to my desktop. And here we are.
Mhm.
And now I will go to the presentation. And now I will share the screen. I'm just talking myself through it
That's good.
so that I don't make any mistakes.
That is just fine.
And
So you want to enlarge it so we don't see your upcoming slides?
now, do you see full screen?
Full screen.
Very good. We are there.
Screen.
So Dr. Luxton, Arthur, and Desmond, if I may,
Yes.
thank you very much, and Alana too for the introduction. I'm very pleased to be with you. I know how good your students are and how interested they are in the world. So I want to give them, you, a different view of chemistry than what the students, you, are likely to have from your imagination, from taking the courses. And we'll see in what way it's different. It's the same chemistry, but there is another cross section that I'll take across it. And I will make eventually clear by the end of the talk what I mean by the essential tensions, and also the three views will come into focus. So here is the first definition of chemistry that has been in there with us for thousands of years. And this is the art, craft, and business before it ever was a science of substances, of things, of materials, of matter. And I need to give you an example. So why not give it from culture? So here at the top are three masterpieces of world art from ancient times. At left, a wall painting from Thebes in Egypt. At the center, the gate of Ishtar, which once stood in Babylon, and then through a feat of imperialism for a change not American, but German, wound its way to Berlin, where you can see it today. And at right, you see a piece of Hellenistic wall painting, a period of realistic representation. This is from about 200 of our era, a period of realistic representation which antedated the Italian Renaissance, which is where we think realism in painting came about, by a mere 1300 years. Now, there is a green or a blue in these, and that green and blue is a pigment. It's a pigment used in painting, in these cases in painting on walls or an enamel in the Gate of Ishtar. And that green, which has in it a blue, came from an interesting source, because all along there was a natural blue coming from the powdered stone or mineral of ultramarine called lapis lazuli as a gemstone. And that blue ultramarine was used whenever painters or artists had enough money from their patrons to be able to use it. So for instance, if you go to Italy and you go to the Scrovegni Chapel in Padua, you will see some beautiful mural, some beautiful paintings painted by Giotto with the ultramarine. But the blue in all three of these works of art up above is not a natural product of ultramarine. It's a product of chemistry, which preceded the existence of chemists. It's Egyptian blue, which was an article of commerce from about 3,500 years ago throughout the Middle East. And it's a byproduct of Egyptian mastery of glass and enamel. It's essentially a glass into which is incorporated a blue copper mineral of one type, of the type of malachite or azurite that one uses in Southwest jewelry, for instance. The blue is in there, and then the glass is powdered and then becomes an inorganic pigment. We now know its structure. We know that the color comes from copper, but that's not really what I want to talk about. I want to talk about that there were chemistry before chemists. Okay? One didn't have to wait for them. People have been put on this earth to transform it, for better or for worse.
Do you think we'll ever find any new minerals?
Excuse me?
Yeah, now
What was the comment?
go
Do you
ahead.
think we'll ever discover any new minerals?
Sure. Yep. But interestingly, one of the interesting things which is relevant to your question, you might have thought that the planetary exploration would lead to new minerals, but it doesn't. Fortunately, it's all the same minerals by and large, which makes you confident that chemistry is one throughout the solar system.
Did you hear about helium-3, about China finding it?
So could I just jump in? We will wait.
No,
till-
mute up. Thank you.
Yeah, we will wait
Mr.
till-
Hoffman, did you hear about the helium-3?
I haven't heard anything. Helium-3 is an isotope of helium, and there are some compounds of helium and sodium in high pressure. But let's leave that for the questions, or I'll never get through my talk. Then we'll have some time, maybe. Also, whoever asked the question, it isn't hard to find my email on the web. It's not a secret. And you can write to me about that too. Okay, so here are the substances that I wanted to make the point that they were there on Earth, and they were traded. They were made in the families of craftsmen without waiting for chemists. Yes, they were made by chemists, by proto-chemists, if you like. And then they were sold and traded, and they were there. Chemistry was and is the art, craft, and business of substances and their transformations. So it's not only A, B, and C, but it's A changing, so that the reaction I've written, A plus B going to C plus D, And for the chemists in the audience, I know there is an arrow pointing the other way for equilibrium, but this is not a bad summary for a reaction that goes mostly in one direction. This is chemistry. So if you had a substance, I'll give you an example. Here's bromine, a reddish liquid and a gas. And then next to it is aluminum. Both of these substances were made pure, 2 elements, at the beginning of the 19th century. And then they could be made. Humphrey Davy made the aluminum first. I think the bromine was around the same time. If you put one into the other, you get flames, smoke, foul odors, absolutely everything you expected of chemistry, isn't it? And at the end, there is something totally different. There is a white, complicated aluminum bromide, complicated aluminum hydroxide bromide at the end of this. So these are transformations. Those are also essentially part of chemistry. Now, I right away have to say that those are the spectacular things, the explosions, the colors, the crystals, but chemistry is also taking place all the time in living things. Here are 2 trees outside the building. I'm actually sitting in a room on the 2nd floor of this building at Cornell University. In the front is a copper beech at left and an oak tree, both planted about when this building was built 100 years ago. And so that's what can happen to a tree and when you take care of it. But in these, there are remarkable chemistries going on in a very...
Lily, turn your camera off.
Okay, so now...
Thank you. Thank you so much. Have you heard about helium-3? China just discovered it on the moon.
I think let's save that question till later. So this is one of the initial definitions of chemistry. But with time, we've learned to look inside the innards of the matter. And without waiting for microscopes,
David, stop mouth breathing. Stop mouth breathing, David. Breathe through. Save some oxygen for the rest of us.
Let's see. Desmond, could you control the audience a little bit?
I think the meeting is hacked. That's why you're getting interruption.
I see.
Yeah, so
You're probably right. It has been disrupted and hacked. So there are several things to do. One is we can start all over again. You can try, meanwhile, from Desmond's side of muting everyone except for the speaker. I don't know if this will work. Desmond, can you do that?
Yes, we are working on it. I have some co-hosts helping me with it. So we'll get control of things here pretty soon.
Okay.
You can go ahead.
I will go ahead.
Yeah.
With time, we've learned to look inside matter, and we've learned that inside substances undergoing transformations, there are atoms, and much more interesting is there are persistent groups of atoms called molecules. So let me show you a picture of a model. You have to realize that these are models. These are like marshmallows and sticks. These are not the real atoms. And of course, these are in large, very large in this case. But I want to show you
Mr. Hoffman.
Yes.
Yeah, it's still, go ahead, Professor.
No, I can't go ahead. I mean, it's not comfortable.
Okay.
So we're going to stop for a while until we clear this up.
Okay.
From my experience, one way when the meeting has been hacked to get out of this is simply to stop the whole meeting, everyone to get out, and then you send to everyone a new call for a meeting. And sometimes that works, but
Okay.
if you have from your professional some advice on what to do, otherwise, I'll be glad to start again, but I really don't want to go on.
Yeah, I understand. So for my co-host, one of the things we are going to stop doing, do not let anybody else in. So don't let anyone else in at this point. We've kicked out 1 or 2 people that we think the problem is coming from. We are not letting anybody else in. Do you figure out what's going on? Hold on.
Hi. Can you hear me?
Yes, I can hear you.
Okay, I would like to ask one of our Andrews students who is not a co-host. So you know if you're a co-host. If you're not a co-host, try to talk because I've muted everybody. I'm hoping nobody can talk except for the co-hosts.
You also did what?
Yeah, I'm getting up arrows. So they have tried to talk and they can't.
Okay,
So let's assume that I've successfully muted everybody except for the co-hosts.
okay. We'll We'll give that a shot. Thank you, Dana. So we'll go with that.
Can
Yeah.
you hear me? This is Roald.
Yes, we can hear you. We
Okay.
can hear you.
So I'm so glad we are all applying the right degree of tolerance and patience
Yes.
that our heritage tells us to do.
Yes. Thank you. Thank you for being patient too.
It's okay from my side.
All right. All right. Let's go ahead
Shall we
and
try again?
yes, let's try again.
Okay. Good. So where I was I was talking about chemistry being the art, craft, and business of substances and their transformations, the changes in them. They happen in living things as well as in inorganic things. I also wanted to go on to say that we have learned how to look at a microscopic level in this, in matter that undergoing change. And there we see atoms and groupings of atoms called molecules. And every chemist is today thinking on both levels, both the macroscopic one of substances and on a microscopic one of atoms and molecules. And the transition between the two is one of the miracles of what one learns about in learning about chemistry. Here are some models of some molecules. And as you see, I have chosen them to be platonic solids or polyhedra, tetrahedral of carbon with one hydrogen out from it, a cubic molecule, one that's shaped like a dodecahedron, then finally at lower right, a molecule that should be on the flag of Brazil, and that's Buckminster fullerene, C20 in the shape of a soccer ball with no hydrogens at all. These molecules are simply beautiful, beautifully simple. I don't have to tell you why they are beautiful. And they are also, incidentally, devilishly hard to make. Some of them, all of them, actually. It's interesting that the last one chronologically to be made, they were all made in the 20th century in the laboratory. The last one of these to be made chronologically is Buckminster fullerene, the one shaped like a football, like a soccer ball. But that one, which is the last one to have been made, is actually today the easiest one and the cheapest one to make of these. Now, in that is a lesson for young people, which you can think about what that implies in a way, about the way of our process of discovery. But the moment I show you these molecules that you see here, I feel guilty. The reason I feel guilty is that, in fact, they do have a direct beeline into my soul. I don't have to be told they're beautiful. And there are other molecules I know. Here's one, which has over 9,000 atoms. And it has 4,500 hydrogens, about 2,500 carbons, a lot of nitrogens and oxygens, 12 sulfurs exactly, 4 iron atoms in those little platelet-shaped tomato-looking like platelets that you see 2 of. There actually are 2 more hiding in this molecule. This molecule is clearly does not have to be, is not simple. It's not like these. And I had to be told about this molecule. This molecule is the biochemical molecule that we know most about, more than any other biochemical molecule. It's the hemoglobin molecule. I don't need to hide it from you. It's the oxygen carrier in our blood. Here is a simplified version of it, and you can see that, let me put with a pointer, you can see it now curled up. All the hydrogens have been removed, and the platelets are still there, but they're now in green. Now you can see them very clearly. The four heme groups, as they're called. And at the center of them in orange is an iron atom. And it is at that iron that the oxygen is bound as this is carried in our body from one place to another. And a mistake in one of the 146 amino acids in each of the 4 subunits, 2 red and 2 blue of this molecule, is what is responsible for sickle cell anemia. So we know an awful lot about this, but the point is that it's complicated. You have to be introduced to it. It's not obvious. And in that is a lesson, and I'll come back to that too. I just want to tell you that most of chemistry is neither hemoglobin nor cubane, okay? Though a lot of it is hemoglobin-like. Most of it is on the level of molecules of this type of complexity, which look pretty complex anyway. This is Taxol in 2 representations of 2 models. Taxol is a component of the anti-tumor pharmaceutical agencies. It originally was isolated from the bark of a yew tree, and the 300-year-old yew tree yielded in the initial finding of this molecule and its activity, yielded enough doses for 3 doses to a cancer patient. It is obvious that you are not going to make a drug by making it from the bark of old yew trees. It has to be made in some other way. And how it's made that way is another story. It's a great story of ingenuity and achievement of chemists. But here I show it just to you, just to show you the middle level of complexity. It looks complex enough, but it's somewhere in between this and the protein. Now, I want at this point actually take a little excursion about simplicity and complexity, because this is interesting by itself. And it's also something that comes up in other parts in our culture. For instance, in what we do, well, you can see that these molecular models of the 2 types that you see here, that they are somehow, they define a structure. And chemists, in fact, talk about chemical structure. The word structure or naturally leads you into building structures. If not houses, then molecules. Different kinds of building. Very interesting how different the 2 kinds of building are, but they're building. And in thinking about buildings, that's architecture, one thinks about simplicity and complexity. Let me make the point in another context. There are some buildings that I don't have to tell you they are beautiful. Here's the Taj Mahal, a high point of Mughal architecture in old India. And you can see clearly the bilateral symmetry emphasized in every point of its architecture. This is simplicity at work, like in the cubane molecule. On the other hand, here is a piece of Rococo Baroque architecture. This is the cathedral in Granada. I'm sorry, did I say Granada? Actually, this is wrong. It's Toledo in Spain. And this is the passage at the top of the altar hall to another hall. And out from that passage, you can see suspended a variety of structures. This is a different aesthetic at work from the aesthetic of the Taj Mahal. This is the aesthetic of complexification. If anything, if any line can be made curved, it will be in this architecture. And this is not what is happening in Taj Mahal. You don't have to go there. You can go, for instance, to structures in South India at Madurai, again, where you have simplicity and complexity contending with each other. And actually, in there is another clue to something I want to tell you, and that is, where does beauty reside? In molecules or in structures? The structures, like the Taj Mahal and the Cathedral at Toledo, they are 12 orders of magnitude, 12 powers of 10 up in size from molecules. But still, when we think about them, we think about the struggle between simplicity and complexity. And perhaps I can define that struggle, which is where I think beauty resides. Beauty does not reside. If you think that beauty resides in simplicity alone, that's actually a misconception in a number of ways. And it does not reside either in chaos. I think beauty resides in the complex borderline between order and chaos, between simplicity and complexity, where the two contend for each other to get into our mind and to have some meaning. I show this to you only because I think it's easier to show this I could show it to you in a molecule, but I show it to you in a simple piece of architecture that Antonio Gaudi built in Barcelona when he built Park Güell. And there's a bench. You can see the bench here. You can see the seats in the bench. There's a mosaic that his friend Jojo did. And the mosaic has in its shapes, which you recognize as symmetrical circles and diamonds. But notice that some of the circles are white and some circles are brown, and they're broken up in a certain way. No two are the same in this structure. I assure you that Antonio Gaudi could and did on other occasions build architectural pieces made out of perfectly identical black and white diamonds. You can imagine what that would look like. And what I want you to imagine is how much more interesting, how much more beautiful this mosaic is, because of the asymmetry that is built on top of a foundation of symmetry. The foundation of symmetry is that repeating curve of the unit. So it's interesting to see these relationship between art and science here. Let's talk about something else, and that is a third view of chemistry. So the first view was macroscopic. Another one, microscopic, atoms and molecules. And then let's go somewhere else, and that is, let's go to how people think about chemistry. And there is going to be no sugarcoating here. There is some, I want to look at the reality of how people look at chemistry. So let me first start with something old just to get there. Here is a 1942 Donald Duck comic book. Only a few people in the audience will remember that time, or will know what comic books were. But these comic books were drawn by one person who did all the text, and this was Carl Barks, one of the original members of the Walt Disney stable. He did this all by himself. He told the story and he drew all the pictures in the comic book. Today, you'd have 150 people working on this with computers. Now here is, I don't even show you what's in that comic book, but what happens is Donald Duck comes in, the nephews are doing some chemical experiments. No one is wearing any safety glasses. This is 1942. This would never happen in a modern chemical laboratory. Donald Duck does something stupid, an explosion follows. He gets the proverbial egg on the head. And then what's interesting is he says, if I mix CH2 with NH4 and boil the atoms in osmotic fog, I should get speckled nitrogen. And the nephews answer appropriately. He's talking chemical talk, but he knows nothing about chemicals. That's right. And this is a picture of that time. What's interesting about this and why I enlarged this particular panel in the comic book is that this experiment, and so the chemists in the audience might wonder why about this or think about it, about mixing CH2 with NH4, that experiment has not been done to this day. So that Donald Duck is actually suggesting, take it literally, a scientific experiment. That's not why I show you this picture. I show it to you for fun, first of all, and second, to make the point lightly, which is not a light point. And that is that in the public perception, from the time of the 19th century, chemists are the people who make things go bang. They cause explosions. And that was not helped in another line when poison gas was used in World War I. So that was a part of a mixed image of chemistry. Now, of course, explosions of the type that Donald Duck does in a laboratory do not happen in any real chemical laboratory. Explosions inherently are a waste. What's produced is not what you want under controlled conditions. Whether it is making that Egyptian blue that I showed you in the first slide, or whether it is making some pharmaceutical, you want things to happen the way they should happen. They don't always happen 100% of the time, but you try to get it right. And that happens even more so when you run a big chemical factory, as shown in this other picture. So explosions are not what one wants. But I want to shift to something else. And now we are today. So what I've done here is I've gone to the Andrews University webpage and I've borrowed a page from your library. And amazingly, I want to use it to show chemistry. The point that I want to make is that absolutely everything you see here, from the rug to the pseudo wood desk, to the glass in front there, to the clothes that people are wearing, the masks and everything else, these have been produced, are the products of our technology. Ultimately, there is a chemical manufacturing step somewhere in them. This, incidentally, this is a word for the chemist, is why, as a chemist, don't ever worry about being unemployed, because there is always going to be a need for you to do what? To transform matter, to sell it for useful purposes. But something else has happened in the last 50 years since the time of that Donald Duck comic book. And that is that our concerns have shifted to the effects of these transformations of matter. So what has created this Andrews University scene, which is nothing special about Andrews, it's a normal human theme here before you of a library, a good thing. It's something which has enabled knowledge, but it has done so by producing a variety of things. And in a process of production of them, we encounter this, which is waste. And in a sense, the analog of the explosion that we saw in a Donald Duck, but now the emphasis has shifted. The emphasis has shifted to the potential harm that we have realized only really in the last 50 years. And there are some people who still don't want to realize it. The potential harm to our bodies and to our planet and to the environment. And this has led to a twofold image of chemistry. That is, we want this. We don't want this. Okay, so it's always the other guy who produces this. You gotta stop that. The other guy is us. And yes, you can stop the misuse of the things that produces the waste, but out of the back doors of the companies that make the pharmaceuticals that cure us and feed us and make life possible in that library, there comes waste inevitable that should be recycled, but is not. And that is the problem that we have. One of the things that gives another image of chemistry. And the second one has to do with something unusual about chemistry. And that is that molecules can at the same time be useful and harmful. And it is sometimes not any different molecule, but it's the same molecule. So the example here is morphine. Anyone in this room who has had a major operation will know what morphine is good for. It is given to you as a first-line painkiller and has tremendously benefited older people and dying people in facing immense pain. But morphine is also addictive, and a derivative, heroin, is deadly addictive. And another substitute for it, fentanyl, another analgesic, has also found its role on the killing fields of drug addiction and of opioid addiction. And it's the same molecule. The same goes for ozone, which saves from ultraviolet radiation in a thin layer spread out in the upper atmosphere, but at sea level is a component of photochemical smog. It's not the different molecule, it's one and the same molecule. Now, let me just right away jump to one of the points. So does it bother you that one and the same molecule is harmful or hurtful? Well, I want you to think about people. Are people all good? Are people all evil? Please, don't expect any more of molecules than you expect of people. People are a mixture of things. There is no question what we would want people to be or what we would want molecules to be. But in some ways, molecules are very much like people. The point I wanted to make is that today we live, remember how I introduced this? I was going to tell you about how people think of chemistry. So I think there is a two-faced, a Janus-faced image of chemistry, of doing harm and benefit. And I think we have to live with it as chemists. And I say it's okay. Not everyone agrees with me that there is this twofold image, because it makes you think more of molecules as being closer to human beings. But I actually want to use it for something else. To me, this harm benefit, this is what you see in morphine, the two pictures. That harm benefit picture is actually part of a broader picture. And that gets me to the last part of my talk. That's where I talk about chemistry is essential essential tensions. The harm-benefit duality is part of a duality or a tension that gives a certain power to chemistry. Let me put it another way. When someone hands you a vial of morphine, you worry about it being addictive, and it is an analgesic. There are two effects. So it turns out that that happens in the rest of chemistry. I just wanted to mention here in passing, I don't mean to go over this slide. I just wanted to mention another reason why people also are bound to feel ambiguous about chemistry, and it doesn't bother me. Remember when I started telling you, I said chemistry is all about change? It's A plus B going to C plus D. Okay, could people ever be anything but ambivalent about a science, chemistry, that is so fundamentally about change, essential change, A plus B going to something else that's C plus D? Why would they be ambivalent about this when they think about this metaphorically? Let me put it another way. How do you think about change in your life? Yes, when your roommate plays a melody for the 10th time, you want them to change it on their player. You do want to change. But how do you feel about changing your school, your profession, your partner or boyfriend or girlfriend? How do you feel about changes that are big and essential? So I think the answer is that human beings are a mixture of conservative and adventurous elements. They want stability. They want stability desperately, but also they want change. And in some ways, chemistry, by being all about change, is in some ways dangerous, or it touches upon something metaphorically. And I am bound, as you can see, to think about these material things in terms of metaphor and art. I am not going to go away from it because I'm one human being. And I think about this metaphor, and the change metaphor is interesting. It's not obvious. What I really wanted to tell you is about essential tensions. Is that as I have thought about chemistry in terms of dualities, like harm-benefit is one. Or one I told you about was symmetry, asymmetry. I also told you about simple and complex. As I think about these dualities or polarities, to me, and as I examine every fact of chemistry in terms of these dualities, is hemoglobin simple? Is it complex? Is hemoglobin harmful, beneficial? As I think of it in terms of the dualities, the molecule or whatever I think about becomes more personal, more interesting in some way. It is no longer an inanimate piece of matter that's something that I have to reproduce on a test. It comes alive in its own way. Let me tell you about some of the other dynamics here. We've talked about simple and complex already. We've talked about these pigments, but now what I want to talk about, these two pigments, ultramarine and Egyptian blue, is one of them is natural and the other one synthetic? That's interesting. Those are two of the things that happen in this world. Here is another one, natural, unnatural. Everyone seeing these two pictures and classifying them would say the chemical plant is unnatural and would say that the plants of the allium family that you see at the left, which make life, that aspect of life, which is taste, interesting, onions, shallots, garlic, and which play an important part in the cuisine of every culture around the world with differences around it. Everyone thinks those are natural. Well, yeah, are they? Interesting. One garlic plant is natural. A field of garlic is most definitely not natural. It's agriculture. And agriculture is a very interesting thing where human beings artificially and synthetically use living organisms to do their bidding. It's part natural, it's part synthetic. It is not a wild growing garlic plant. Other things which we don't think about at first, think for instance, to reveal or to conceal, that duality, is that something we should worry about in chemistry? Of course. When you invent something new and useful, like the modern day equivalent of an, let's say, an antiviral drug, do you patent it? Or do you treat it as an industrial secret, its manufacture? Patenting is a very interesting human invention. Trust and skepticism are very interesting, always in balance. We believe what other people find in science, but we always mistrust it to a certain degree. And these are all things that make life interesting. So now I have come to my end here, and that is that I've told you 3 views of a science. I hope that these are not the ways that you have thought about chemistry in the past, but I hope that I've given you different ways to think about chemistry, and especially to show you ways in which chemistry comes to life, not because it produces life or tries to or anything like that, but because of the tensions that are in it, the polarities that are very much like those that we face in the real world. I just want to, I'm going to take just 5 minutes more to just show you something else, if I may.
Yes, that's
yeah.
okay. Mm-hmm.
Okay, so you've seen me use science and art as illustrations throughout. And I want to show you something else here. I want to show you this because I want to leave a certain message to young people. Here is the icon of chemistry, periodic table of the elements. Could talk about this for a long time. This is not the way it was drawn initially. When one looks, and this is a job for historians of science, for how Mendeleev constructed this in 1858. He had to write a textbook. He felt the pressure to write a textbook. He had already been thinking about the elements, and he wrote down the periodic table. I'll show you the periodic table in just a minute. When he was asked about how he did it, he told the story. So here's the story Mendeleev told. He said he wrote out the recently agreed on atomic weights of the elements. The elements weigh different amounts. An oxygen atom weighs 16 times as much as a hydrogen atom. So he wrote these down, the elements, in order of ascending weights. And then he looked for similarities so that bromine was like chlorine, like fluorine. And he rearranged things into the geometrical pattern that you see approximately here. Well, it's a good story. It got better every time he told it. He was asked to tell it many times. People liked his work. But no one has ever found the cards on which Mendeleev said he wrote out. We don't know what kind of playing cards they were, blank or with the actual suits and values on them. No one has ever found the cards. When historians looked in his files, this is what they found. Okay, so now bear with me while I take you through a page of Mendeleev's notebooks, which is the first appearance of the periodic table. And here in the middle is the periodic table. You see here the element symbols: fluorine, oxygen, nitrogen, carbon, boron, beryllium. They were already there for 30 years, invented by Berzelius, designed by Berzelius. This table, all you have to do is to turn this by 90 degrees, and you will get the periodic table that you see in at least the part on the right that's over here. You see here, B, F, O, N, C, B, beryllium. So that's what's in here. Now, what else is going on here? First, at the bottom is a laundry list. So when someone asks you to put things in order, that's the elements. So what you do first in order to stall for time is you make a list of the elements. So he makes them one by one at the bottom of this page. And as he fits them in a table, he does what any human being would do. He crosses them out. He's writing in a mixture of German, über here, and Russian, because he studied in Germany. And there were 3 elements über, these were left over, 3 elements that he couldn't fit in. He makes them fit in. It is in the nature of theoreticians that they make things fit in that don't fit in. This is absolutely amazing. And what is the most amazing thing about this? The most amazing thing, of course, is the crossing out. This is the prima facie evidence that this is done by a human being and not by a machine. This is the evidence that Mendeleev is not a robot. I can say it in today's language, but it's wonderful. And I hope that everyone here sees this, but I'm not quite finished, because, okay, this is science. This is Mendeleev in the process of discovery. And incidentally, historians of science are terribly, terribly worried about computers, because the evidence of the work will be gone forever, like this, when we don't make our hand scratches on paper, as Mendeleev did here. Okay, the point I want to make is that we are so funny human beings. We see this and we see before us the evidence of humanity in its creation. It's wonderful. And then we think somehow there must be a place where perspiration doesn't count, but inspiration does, okay? And the usual focus for such romantic notions about human beings are poets. So people think that poets, that's me in a certain part of my day, go walking around the whole day around campus doing nothing. And then every once in a while, they flip out a little notebook like I have in my pocket, and out comes a poem, fully formed like Athena's, like Athena's brow, fully formed. Well, let me show you. Here is a well-known poem from the English language, The Tiger. Tiger, tiger, burning bright in the forests of the night, what immortal hand or eye could frame thy fearful symmetry? This is William Blake's. Here is the last draft of Blake's poem.
Mhm.
It's in a Bodleian library in Oxford. That mark, which goes down over the whole page, that's the printer's mark. That means he set it from this manuscript of Blake. And there are several drafts before this, but we don't have them. And he has tiger, tiger burning bright in the forest of the night, what immortal hand or eye. And there he has first dare grasp, and then he puts frame instead. Then he changes his mind and he uses the dare grasp. He changes it to dread grasp down at lower right here.
Mm.
And then he doesn't like that, so he restores it. Dare frame thy fearful symmetry. Science is not literature, but when you see these two things
Mm.
side by side, I hope you see that here's what I see in them. First of all, I say, these are objects of human creation. And until you try, you don't get anything. But when you try, you get something.
Mhm.
So you have to put your pen to paper. That's what you have in part. There may be someone forcing you to write a textbook like Mendeleev. In Blake, we don't know what, I don't think anything forced, but you try. And then you get something and you settle on it and you're unhappy. It doesn't feel finished. It doesn't matter. It's finished for now. It's good enough. It's human. The other thing is that this, as the crossing out shows you so explicitly, this is accessible to absolutely every human being on earth. And for the students here, it's not only Blake and Mendeleev, it's you. This is accessible to you. You can create something new. Thank you.
Wow. Just like, wow. Very, very good. Thank you so very much. Alana, you want to unmute, Alana?
Yes, can you hear me?
Yes, we can hear you. So here's what we will do, Alana, and some of the other co-hosts could help with this, is for the question and answer period, we'd like people to raise their hands. Then once we recognize you, we could unmute you. And we want to do it in a systematic way so we don't run into any problems like we did. Unfortunately, we have to take care of this kind of business, but this was a great, very inspirational lecture. And do you have a question, Alana, to get us started?
Sure, yes, I do. So Professor Hoffman, something that you said in the lecture particularly caught my attention, and I thought it was very interesting that you drew the difference between trust and belief. You mentioned that we believe what people find in science, but we always mistrust it. And I thought it was very interesting that you differentiated between those two things. So I was wondering if you could elaborate on what that means for you in the field of science and perhaps also in life.
Yes. So I think the trust and the skepticism are reflected in the way we use footnotes and citations. So when you cite somebody, you are putting, it's not that you're shifting the belief in somebody, but you are using somebody else's finding with confidence and trust. Maybe you are distancing yourself a little from it because you're giving it the name of someone else. But basically, I think an act of citation of a quote in a talk or a paper, or a citation in a paper, is an act of trust, but it's also a little bit of a distancing, saying that somebody else has done it. I think we are that way in life. One of our problems is how to build a degree of skepticism about what we do ourselves. That's the hardest thing to do. Though there are some people psychologically who have trouble thinking about anything that they do being good, but actually most of us do not doubt enough our own conclusions about something. Fortunately, one of the beauties of the system of science is that it's full of people who have ideas and are not particularly good at exhibiting enough skepticism about their own ideas. But there are other people, and as long as the system of science functions, those other people will call into doubt what anybody offers as a theory for something. And the science as a whole will progress in that. So it's very important to have an open system where different opinions are allowed, and one is not penalized for having contrary opinions.
Okay, so I see Lily's hand up. Lily, you want to unmute? Unmute.
I don't know if you, oh. never
Okay,
mind.
there you go.
I just got the ability to.
Okay.
Yes. So, yeah, Dr. Hoffman, when I was a junior in high school, I read an interview that you did with Liberato Cardellini in 2007 for the Journal of Chemical Education. And it made such an impression on me that I almost studied chemistry. I didn't, but I almost did. And in that interview, you compared the way that chemists make molecules to the way that artists make art. And that just made such an impression on me. So I wanted to know, in your personal creative process, the way that you write plays and poetry, does that creative process inform the way you make molecules or the way that you do your chemistry?
That's a good question. So it's okay if you didn't become a chemist. Yes, so the question also can be put in another way. What way has your science informed your poetry, and vice versa, in the other direction? So certainly so I'm a writer. I'm not a visual artist, so I look a lot, as you've seen from those slides. I look a lot at art. And when I was in college, I almost went into art history instead of chemistry. So, but the poetry has certainly made it easier for me. I always had an easy time in writing and science, but it's made it still easier. It's made me recognize the power of brevity, of abbreviation, and the power of metaphor.
Mhm.
And the one thing that the arts and in literature, especially poetry and also novels do so well is to use emotions as to touch on the emotions and as a kind of currency. And in science, for reasons that have to do with the history of science, we have gotten into ways of, if not devaluing emotion, of not allowing it in some ways.
Mhm.
But I learned early on, and I learned it actually not so much from the poetry, but from teaching introductory chemistry, that if I could establish, even in a large class, and at Cornell is not like Andrews, there are classes here that have 1,000 people.
Mm.
If I learned that even in a large class, if I could establish some emotional contact, very carefully it has to be done with the students. The emotional contact is in the direction that the students realize that I, as a teacher, really care that they understand.
Mm.
But I won't get angry if they don't understand. Okay, because that'll turn them off.
Mm.
Because then I'm behaving like a parent. And but that personal contact, and you have to be very careful about this. So various teachers have this. If you look too closely at one student in a group of 100 and you keep on looking at that one student, that student's going to be very uncomfortable and the other students are going to notice it anyway. So what you have to do is you have to look at a dozen people and keep changing your focus.
Mhm.
In some way between them, but that the student understand that the teacher care.
Mhm.
There are various ways to show this, not just by looking at a student, but in making a chance remark like that. You assign a homework problem and you say, I understand this is a difficult problem. If you just say that. Okay, so I learned from that making emotional contact with the students was very important in teaching. And then I learned this. I applied some of the lessons of poetry for making emotional contact for the audience that's listening to the poem or reading it. That if I could make that emotional contact in my writing of a scientific paper, now that is really hard to do.
Yes.
You are told to write it in third person neutered.
Yep.
And you're not supposed to express emotional things, but if you could express some of that which I just described of expressing in a teaching mode, if I can teach in a scientific paper, if I can make them feel that it's important for me that they understand those molecular orbitals, and I start using, if I can sneak in some anthropomorphic language about the orbitals, this level is repelling that level. There's a little bit of anthropomorphic language.
Yeah, yeah.
Levels don't repel each other, but talk about it that way. I've got my chemical audience and I've established a style of scientific writing. And I found actually that after I began writing poetry, this was easier to do. I can't quite tangibly put some finger on it, but I was able to inject some emotional language without much overtness
Mhm.
into the writing of the science, and it made an impact. The other thing that I did was I was clear as I could be. And I kept saying, this is difficult to explain. And I tried to do it. Sorry, I went on for quite a while.
That's okay. John Juan, you got a question? Unmute. Unmute yourself, John Juan.
Oh yeah, sorry. Someone had the
Yeah.
thingy on, so we didn't want it to echo.
Okay.
So you talked about the many dualities of chemistry. What's your thought on a chemist like Fritz Haber? You know, even though he saved the world through ammonia synthesis, he
Yes.
also contributed to the poison gas program. How can we try to obtain only the goodness of a chemist, or is this impossible?
Oh, he was caught up in many dualities. Poor Fritz Haber.
Yeah.
He was Jewish, he was not Jewish, he was German. And some of the dualities were not of his making. But he's a tragic figure. That's clear. At almost every aspect of his life is tragic. His relationship with his wife, and then the end of his life as Hitler came to power and dismissed the Jews from the universities. What can one say? Haber lived out a difficult life. He is not, he certainly devoted his life to the First World War German machine, but how much we should fault him, I think he didn't see the problems with poison gas. You know, poison gas is one of these things. He started out with chlorine, then it turned into other gases. The Allies had quickly the chemistry both to, not to stop entirely, but the particular way of dying was horrific. And it's that which made much more of an impact than the actual military value of the poison gas, which proved to be, in the end, totally indecisive in World War I. And in no war since has it proven to be of value. And yet it remains, there is something about no longer being able to breathe.
That's very frightening.
Which is so terrible. And you know, in describing the effects of COVID, this is also the thing that I think frightens people as they are described more than anything else, is of being unable to breathe.
Yeah.
Because it's such a basic human thing to breathe. Okay, I didn't answer your question. Haber is a complex figure. He remains a tragic figure.
So do you think that in teaching chemistry at all of the levels, from elementary to university, we should at least try to humanize it more, give more history? Because that seems to be, these sort of stories you just talked about with Haber and others, seems to be like totally missing in grad school for sure. We focus on mechanisms and, you know, yeah.
In grad school, a particular place where they're missing, and they're replaced by mythical chemical structures like the discovery of CC coupling and
exactly
chemical story told around it, but there are names attached to it.
Yes, name
the
reactions, yes.
chemists that are, but there's no human story
No.
attached to it.
Yeah.
And so you mentioned history. So history of chemistry should be taught at every level. One has to work to make the students feel that this is in some way essential and not just color, which will not be on the exam. And that has to be made clear how to make it, how to tell those stories well is an art.
Right.
It is an art.
So, yes.
There are more and more popularized accounts where we can talk about these things.
Yeah. Maybe one last question. We're getting up here on 6 o'clock now. One last question. I think we will wrap up after that.
Yes.
Novak, you seem to have enjoyed this really a lot. Do you have any questions swirling around in that head?
Well, no, exactly, somebody's got their hand up, but all I can say is I deeply appreciate you talking about the connection of the symmetries in the arts and how that's connected to science and fundamentally connected to human creativity. It is, I think it's very valuable, especially for someone starting out new, like the students here, that they should open their eyes. I think it's sort of like you were revealing things that were hidden in plain sight. Okay. And beginning to think outside that narrow frame that we teach in. And it truly is inspirational. And I'm grateful. I don't have any questions other than to be humbled by the fact that we are a species that can think and to do and can create, and we can also destroy. That's our dichotomy. But to be able
Gifford, it seems like Gifford, Ralph, you have a question? You want to unmute and we'll take your question?
Yes, I do have a question. Can you hear me?
Yes, we are hearing you.
Yes.
The last question.
Dr. Hoffman, what is your favorite element on the periodic table? I figured you might have some since you were talking about knowing them personally.
I know them personally. So I like silicon.
Oh.
So the reason I like silicon is several reasons. I have a book which I'd urge you to read. It's a popular science book called The Same and Not the Same. And that's what silicon, first level, that's what silicon means to me. And that is, remember that silicon is right under carbon in the periodic table. And what's the periodic table about but similarity? But no, the periodic table is about similarity that allows difference. That's what's important.
Right.
And so silicon is like carbon. Yes, you form silane, SiH4, as you form methane, CH4. But it's different. I want you to think of sand, SiO2, and CO2, a gas, and dry ice. They are different from each other. And it's that difference. Why are they different? That then becomes the origin of a story, part theoretical, but it's a story of difference. Here's another interesting thing about silicon. You know that life is dependent on carbon and its chemistry. And there have been science fiction pictures of silicon-based life, but it's unlikely for a number of reasons. We can think about it. But the interesting thing is there is relatively little silicon biochemistry.
Right.
But there's a lot. You might have thought that a process of evolution, which would find a place for molybdenum, a weird element. Nitrogen. If you don't know that story, look it up. It's incredible. would find a place for silicon in some enzyme, but there are very few that have silicon.
Right.
Actually, silicon as quartz plays a structural element, and I think some substantial percentage of a rice plant, of a seed, a rice seed, has silicon in it, which is not digested, not used, but that's okay. There are other things that are not used, but which at least contributes to the biology. But I find it interesting that silicon, which is not used by evolution, I'm talking in teleological language, which isn't right. Silicon not used by evolution has reaped its revenge by being used in transistors. Isn't that interesting? That's why I like silicon.
Okay, thank you so much, Dave. Could you take us?
Yeah.
Go ahead.
Lots of fun.
I have the privilege of saying thank you, Dr. Hoffman. I have the privilege of showing you a book you might recognize.
Good book. Only in one edition, never went through a second edition.
Yeah, I keep looking for poetry in it, but somehow I don't see any. However, I do see figures that remind me of art. Indeed. Got this in 1974. I was so impressed with the Diels-Alder reaction and that you got the Nobel Prize for doing so. One last final comment. Your comment about the editing and so on, it reminded me of something that I heard that Mark Twain said, but it actually was Blaise Pascal. He said, if I'd had more time, I would have written a shorter letter. If I had more time, I would have written a shorter letter.
Thank you all. It's been a real pleasure.
Thank you. And we are grateful for your time and your talent.
And we overcame the problem with the troll.
Yes, we did.
Yeah,
thank you.
We did.
Bye.
Bye,
Thank
Alana
you.
and
others.
Bye.
Okay, bye-bye.
Thank you so much.
Thank you, everyone. Thanks.